Okay, so I will first of all try to talk a bit about the scope of what I will be discussing here, because we saw a few applications in optics, and I think they touch different parts of a sort of development flow of an optical product. Where here we go from R&D and prototyping all the way to mass production, essentially. And the scope that I will discuss here is mostly the higher volume production. And there's several reasons for that. The main reason being that you can actually get more data from that type of application as opposed to an R&D or prototyping approach. There's just more parts, and the use cases that we implement are scaling with the number of parts. So this is really what we're concentrating on. And in that niche, or it's in the field, let's put it that way. Really, what people are interested in is overall equipment efficiency. And at the bottom, you see like one of these larger production lines that we have in the field. And so the overall equipment efficiency that people want is essentially a combination of high yield and high throughput, so UPH, units per hour. If you can increase throughput, that's always a benefit. And low unscheduled downtime, which can also be expressed in terms of availability. And in optical assembly in general, the OEE is really influenced by a lot of things, such as part loading, measurements that are made on the machines, alignments, the maintenance of the machine, and computer vision routines. And generally, you can get data for all of these processes and try to analyze where there might be opportunities for improvement. But in a lot of cases, you can actually leverage the data to directly improve the machine performance. And yeah, this is the main thing that we concentrated on. So just some cases of what we did in the past for some of our customers, mostly in datacom assembly, where we have different use cases. And yeah, depending on the use case and the actual customer module, machine design, et cetera, et cetera, et cetera, there's different numbers you can reach. But the overall take home of this is generally by using data-driven optimization, you can increase OEE by over 20%. Now, this number, the origin of this number is, for instance, if you take a look at the top row, this is exactly 20%, but in the meantime, we developed some use cases that weren't used there. And I think the 20% is a general idea of what can be achieved. Whether or not that is reached depends on how the use cases scale and how much resources you actually put into the project. So because of this, we have developed our own platform for edge computing called ficonEdge. And what you see here is generally how the data flows and what we do with the model outputs. So we have a lot of data coming from the machine going into the edge device. So if you're not familiar with it, edge computing as opposed to cloud computing is when the computation is done on the actual premises. So inside of the device where the data is gathered. So as opposed to cloud computing where it's obviously centralized. So there's generally two paths with which you can use a model output in order to improve machine performance. The first one that we termed self-adaptive production is where we feed the model output directly back into the programming of the machine in order to make the machine faster, or make improve performance in general. And the secondary path is essentially via technical stuff. So in the first case, we don't need any human interaction at the point in time where the model is executed, whereas on the second path, we need technical staff, for instance, to repair things or perform an analysis. It can be really useful for that. Yeah, but obviously the first case has some advantages. So here we have one example of what the secondary case might look like. So here we have some optical probes that are part of the machine that are required in order to perform lens alignment. And in this case, the cleanliness of either the parts or the premises wasn't sufficient to make sure that the probes are not contaminated. So after some time, probe contamination led to false identification of parts as being failed. And as you can imagine, that hurts, because you have parts that would otherwise be functional labeled as being scrap, essentially. So you throw away parts, which is quite painful. And by implementing a model that would identify probe contamination, we would be able to reduce the number of scrap parts by 2/3, which in this case is like a 7-figure saving a month because of high production volume. So I think this is a pretty good example of a relatively simple model that can have a large effect. So the other example I would like to show is adaptive motion, where the premise of that use case really is that motion in a production environment is always a trade-off between having sufficient accuracy of the motion system and having high speed. So overall, obviously, you want to make it fast, but especially with optical systems, you also have to be very precise, and the two are in opposition. And on top of that, in field conditions where you have technicians and other contributing factors like degradation of things over time, or repairs that are being done, et cetera, et cetera, et cetera, the trade-off between the two factors changes over time as well. So in an ideal world, we could measure the motion accuracy in the field and determine whether or not we can make the system faster, or if it should slow down and be more accurate in order to not lose parts. However, measuring that in the field would require us to take the system out of production, which directly opposes the entire purpose of the entire thing, because you lose production time that way. So question is, how do we go about this? And what we did here is implement a model that can predict the repeatability or accuracy of the motion system based on data that we get from both the machine process, but also the really the motion data that we stream from the machine. And here we have a little demonstration of that model, where my colleague Lorenzo added some weight to an existing axis system. So here it's actually running in spec, and we move a little bit back and forth. And what you can see is that when Lorenzo adds the weight, the motion system is compromised. So it's not been tuned for that particular weight. And so what the algorithm does, it detects that the system is not running in spec anymore. As a reaction to that, it changes the motion settings to make sure that it runs in spec after that. It might run slower, but it will continue producing. And that's the important part. It will continue producing parts without losing parts in the process. So it can actually continue production. Let's say something like that happens in a night shift, and you don't have the technician there who can repair things. In that case, you want to just continue production with slower motion settings and have the person repair it the next morning. And here the system can also send an email to technicians so they can repair it the next day. So yeah, another use case, and this is now not what we have on ficonEdge anymore, but this is sort of an independent system that we also offer. And this is really part inspection. And the current state of the art is you have a classification model for good part, bad part. Oftentimes you also can extract like a heat map of which parts the model actually looked at. And the way it's typically implemented is you have large pre-trained neural networks that have been trained on millions of training images. And what you then do is you retrain the top layers of those networks to make it specific to your use case. So you feed it with data, and typically it's in the range of hundreds of images. And since most of these solutions are designed for the really general case where you might have really images from mobile phones trying to identify faces, or you have cases like ours where you really have technical images of technical parts that you want to identify. But the thing is, there's a lot of data in these multiple millions of images that are not actually helpful for what we're trying to do here. So that you can see here is like, okay, on the right-hand side, you have a photonic integrated circuit, which is really, a technical piece or a technical part, and very precisely manufactured. And the data with which those models have been trained is, probably tilted images of chickens. And those are really not the same thing. And the features that those models use may or may not be useful. And so, yeah, what we found is that, not only is the neural network probably not optimal, but it's also some of the conditions where mobile phones can be tilted by 45 degrees, and it should still identify it as a chicken. However, on a machine, you don't arbitrarily tilt your images by that amount. It might be off by a degree or two if part loading is compromised, but yeah, generally there's a lot of conditions that you can bake into the learning process that not only make it perform better, but you also have to configure fewer steps manually. So it takes less expertise to really run those models and make them perform well, because the option that the general tool might offer, where you can really configure and eke out things, a lot of them are really not needed. And yeah, so what we found is that we can get better performance and fewer manual steps. This development is still ongoing, so I don't have any final results, but overall, in some cases, we were able to reduce the number of false identifications of parts by about 50%. So this is relevant, and if you do it properly, you can get good performance out of it. So yeah, specialization works. That's the message. Yeah, and that's all from my side.